Professor Bialis here. In this video we're going to be covering section 10.5 where we rationalize denominators and numerators. Now what we typically do is rationalize denominators. The reason why I have this in parentheses is I am going to talk about that at the very end, how to rationalize a numerator. It's simply the exact same thing, it's just you're targeting the numerator as opposed to the denominator. Most of the time we're going to be targeting that denominator. The numerator only comes up every so often. Right now, the only reason we're showing that to you is so that you know that it's a possibility. Okay, so let's just jump right into some examples to see why we're doing it, what it means, and then how it's done. So let's just jump right into 7 over the square root of 2. Okay, now something I want you to remember here, unless you are told otherwise, never leave a radical in the denominator. If you do, it's not considered simplified. So again, unless you are told otherwise, never leave a radical in the denominator. So in this case, that's not okay. When we've seen that in the past, the denominator always had like a square root of 9 or a square root of 16, something that just worked out nicely. Okay, so when it doesn't work out nicely for us, we need to take care of that radical. Now, why we call it rationalizing is because right now that's an irrational number. Square root of 2 is not rational. So we want to make it rational so the radical disappears. Now, the most fundamental idea we're going to be using with this is what you multiply the bottom by, you multiply the top. Okay? Now, what do we do with this? If we want the square root of 2 to lose its radical, we are going to multiply top and bottom by the same thing. Okay? When we're talking about square roots, just use the same square root. Okay? So what I mean by that is I want to get rid of that square root of 2, so I multiply by square root of 2. Okay? Why did I do that? Because square root of 2 times square root of 2 is square root of 4. I'm essentially squaring that 2 because I threw another 2 in there. Okay? I don't have to think about it as squaring though. I could just think I'm just going to copy that. Because square root of 2 times square root of 2 is just a 2 because it's square root of 4. And then on top now I have 7 square root of 2. Okay? So again, when it's square roots, I just copy that radical. That's it. And then that is a rationalized expression. Notice I didn't get rid of the radical, I just moved it up. Okay, but I can't just literally throw it up top. I have to make this happen on top and bottom. Okay? That's pretty much it. We're going to go into more detail and throw some more examples at you, but that's what we're doing in this section. Let's look at another one. Okay? Now, one thing I want you to always remember, don't just look at that and say, I need to get rid of the square root of 16y. Simplify it first. If you can simplify, simplify. So I'm going to look at this, and not only does that square root of 16 simplify, but also the square root of 9. So I got 2, square root of 9 is a 3, square root of 16 is a 4, and then I have square root of y. Let's clean that up for a second. Now, I don't need to rationalize a square root of 16y, I just need to rationalize a square root of y. That's a lot easier to do. Okay? The other thing that you might want to do at this point is we can simplify these two numbers right here. You could do that at the end, but you could also just get that out of the way right now. All I did was take a couple nice radicals and simplify a fraction. Now, I need to get rid of that square root of y. So what do? I multiply top and bottom by square root of y. When I do that, I get 3 root y on the numerator, and then in that denominator, I have 2, and then this product here. But what's square root of y times square root of y? Y. So I get 2y in that denominator. Nothing more than that. Okay? Let's now look at another one. let's say we have cube root of 2 over 25. Okay. Now, remember what I said in the previous videos. If you have a fraction with one big radical, that's only good when this is reducible, just as a normal fraction. It's not. So better for us would be cube root of 2, cube root of 25. Okay? Now, notice the difference here. We're dealing with cube roots. Now, when we had square roots, we just copied that radical. When we had square root of y, because then that squared it. We had a y squared, we had a 2 squared, and so on. Here, we need to have something to the third power for it to come out of that cube root nicely. Okay? Now, let's look at this, and there's a little trick we can use. I could think of this as 25 to the first, but then I need another 25 and another 25. That's a pretty big number. Instead, watch what I'm going to do. I have a cube root of 2. I'm going to change that 25 into a 5 squared. Make change. Okay? This is all about quantity. I want to have 3 of something. I can either think of I got one 25, like a single 25, or I have 2 5s. Okay? 2 5s is going to be better for me. That's like a single dollar bill or 4 quarters. Same value, but if I'm looking for quantity, the 4 quarters is better. Now, what's good about that is I already have 2 5s. So how many more do I need? I just need to multiply by another 5. If I bring these together, I get a cube root of 5 cubed, because it's 5 squared times another 5. There's your 5 cubed. Okay? And that comes out as just a nice, clean, rational 5. And then in that numerator, I have cube root of 10. And that's the best we got. Okay? Let's look at another like that. Let's say we've got cube root of 6 and a cube root of, let's say, 9. Okay, now, is this always going to be a nice perfect square? No. Okay, if it's not, let's say this was a, let's say this is just a normal 7. Okay? Okay, let's look at this one for a second. If we have that, we need to multiply top and bottom by a cube root. We have a single 7. How many more do we need? To get a 7 cubed, we need 2 more. Now, when we pull these together, we have the cube root of 7 cubed, or just 7. Okay? And now this, we would then have to multiply. Again, if you need to, 7 squared is 49. 49 times 6, that's 54. 24 plus 5 is 29. That is a cube root of 294. Okay? And that's it. That's all there is to it. Okay? So don't be afraid to do this multiplication, and it's just we need a quantity of 3. Okay? Over here, if you can rewrite this as a perfect square, where it's something cubed and we're looking for 4th powers, whatever it is, if you can increase the exponent, great. If not, just deal with it. Okay? Let's look at something else. Let's say that. Again, it would be really nice if this is one big radical if this was simplified. It's not. So let's split it up. We got square root of 5m, square root of 11n. Okay, now remember, we're back to square roots, so we need pairs of things. So all that means is we're going to multiply by that square root of 11n, square root of 11n. Square root of 11 times 11 is just an 11. Square root of an n squared is just an n. And then that numerator, we have 55 mn. Okay, we can multiply the 5 and the 11 because we're multiplying. If it was adding, we couldn't bring those together. Both multiplication, we can. Let's look at another one. Okay. Now, like I said in a previous example, if you can, simplify first. Because then, even if you still have to rationalize, you're rationalizing with less. So what I'm going to do is I'm going to focus down here. This numerator, that's as good as it's going to get. 32. Now I'm looking for a perfect fifth power that goes into 32. It's not going to take much. What is 2 to the fifth? 2 times 2 is 4. Times 2 is 8, times 2 is 16, times 2 is 32. That is a perfect fifth power. So forget about breaking it up. Fifth root of 32 is 2. Now, 5 and 12, that is not going to divide evenly. So I'm going to have some b's coming out, and I'm also going to have some b's staying in. If you need to do the long division to see that, go right ahead. But 5 goes into 12 twice to make 10, but then there's 2 remainder. Okay? And then I have a fifth root of a squared. All I did was simplify that denominator so far. Now, it didn't simplify all the way, so I need to still rationalize. So when I'm rationalizing, I'm multiplying top and bottom by the same fifth root. It has to be fifth root because everything's fifth root. Okay? Now, I need to rationalize this piece right here. This piece is the bad piece I need to take care of. Now, in order to do that, I need to make sure I have 5 of something, because then that's a fifth root. It'll come out nicely. If I already have 2 b's, how many more do I need? I need to have fifth root of b cubed, fifth root of b cubed. Okay? Now that numerator is nice because it's just a fifth root of a squared b cubed. How about that denominator? Let's see how that falls out. I'm still going to have a 2. I'm still going to have that b squared. All of this is going to be a fifth root of b to the fifth. Fifth root of b to the fifth is simply b. So what I get when I pull all that together is a 2b cubed. These cannot reduce because that's not truly a b cubed. That's the best we got. Okay. I like, whenever I have a little bit of some work to do at that point, I like to go off to the bottom of the problem and then continue my results to the side. Okay, but organize it any way that helps you and that works for you. Let's now go on to something a little bit different. Let's say that. Now, what's different about this is that denominator still has a radical, but it has more than one term in it. Okay? If we had square roots in the past, typically we just multiply by that square root of 3 and that was it. But if we multiply by a square root of 3 here, we would have to distribute that and we would end up with a square root of 3 over here. So that wouldn't really solve the issue. So what we have to do is remember back from the previous section when we were just multiplying radicals. There was a certain type of two-term expression times a two-term expression that eliminated all the radicals. Okay? And what that is is when we take the same two terms, and if we're adding here, we subtract here. Again, the same rule applies. What you multiply to the bottom, you multiply to the top. Okay? We just need to know what is going to do the trick. And in this case, again, we take the same two terms. One spot we add them, one spot we subtract them. Nothing more than that. Okay? Now, let's carry this out, and then I'm going to talk a little bit more as to why that works and so on. Okay? If we were to distribute this, remember, radical or square root times the same square root is just going to drop out to a 3. That radicand just drops out. Okay, that's why we want the same term. So if there's a radical here, there's a radical here, and it's going to cancel each other out. Now, what about this though? We got negative 2 root 3. That radical didn't go away. But why did we change the signs? Because now, where those radicals stay, we have opposite signs. And then lastly, negative 4. So these will go away. These terms, the first and the last, will always be doubling up radicals if there's a radical there. So those radicals will go away. 3 minus 4 is just a negative 1. No more radical. Okay? The numerator is a 5 root 3 minus 10. Okay? Now, if you leave it like that, that's not really wrong, but it's not as nice as it can be. This 1 doesn't really need to be there, but the negative, if it's not here, needs to be absorbed into the top. So this is not bad, but a better way to write that is a negative 5 root 3 plus 10. That is the nicest way to write that. Okay? But this isn't technically wrong. Okay? Now, what we did is we multiplied top and bottom by what we call the conjugate. Okay, now what is a conjugate? Same structure we have here. If I have a square root of 5 plus 2, the conjugate would be square root of 5 minus 2. If we had 7 minus root 11, the conjugate would be 7 plus root 11. If I had negative 8 plus square root of 3, the conjugate, careful here, is still negative 8, but then minus square root of 3. That's all we do. When we have multiple terms in that denominator and we want to rationalize, multiply top and bottom by the conjugate. You keep the same two terms, change the sign in between. Okay? Let's look at a couple more examples of this. Okay, so again, the problem that we have here is we've got radicals in the bottom. Since there's two terms, we're not going to be multiplying top and bottom by just a single radical. We're going to be using the conjugate. So I'm going to multiply top and bottom by the conjugate of this, the conjugate of the thing we're trying to clean up. So that's going to be square root of 3 plus root 2. So root 3 plus root 2. I always like to FOIL this denominator out first to make sure all those radicals go away. If they don't, I picked the wrong thing. So let's do that. Square root of 3 times square root of 3, that's just a nice clean 3. Square root of 3 times square root of 2 is a square root of 6. Negative root 2, positive root 3 is negative root 6. Negative times positive is a negative. Root 2 times root 2 is 2. Those cancel out like we expect, and then 3 minus 2 is just a 1. In the numerator, I got root 5 and root 3 is root 15. Root 5 and root 2 is root 10. Root 3 and root 3 is just a 3. And then root 3 and root 2 is a root 6. Okay? Nothing reduces there or combines. So all we have is this expression over 1, or we could simply just write that expression. Okay, and that's all we need right here. Okay? So, let's look at one more. Okay, now we cannot cancel these because this is one quantity that we have to hold together. However, we need to rationalize this. So since there's more than one term, use that conjugate, which is 2 plus root x. Okay? Foil this first. 2 times 2 is 4. 2 and a root x is 2 root x minus 2 root x minus just an x. That goes away. Now, we don't get a nice clean number, but we don't have any radicals. So what we have in that denominator is 4 minus x. And then in that numerator, 4 root x times 2 is 8 root x. Now careful, 4 root x times square root of x. We still have that 4, but then square root of x times square root of x is just an x. And that's all we can do, that's all we need to do. We could factor out a 4 there, but it's not going to bring us to reducing anything, so it's not necessary. That answer is good. Okay? I want to finish up by just saying something very briefly about rationalizing a numerator. Rationalizing a numerator, again, does not happen very often, but sometimes they do ask you to do it, and like in a calculus setting, it might be necessary. So I want you to see what that looks like and how to do it. Let's start with something just very simple. Let's say we have something like this. Now again, in this case, I want you to rationalize the numerator. And let's say we have cube root of 3a over cube root of 7b. Okay. Now it's the same concept, it's just we're targeting the numerator. In this case we need cube roots, so we're looking for groups of 3. So we're going to multiply top and bottom by the same cube root. And in this case we have 1, 3, so we need 2 more. And we have 1a, so we need 2 more. Same thing as we did before, it's just we're targeting the top. The numerator now, we've got a 3 cubed, so the cube root is just 3, and an a cubed, so the cube root is just a. And then in that denominator, we've got 9 times 7 is 63, and then a squared b. That's it. Okay? Again, don't look at that and say, well, wait a minute, he said don't leave that radical in the denominator. Unless you're told otherwise. When they say rationalize that numerator, they're telling you otherwise. Okay, radicals are okay in the bottom in that case. And we have that. Same thing would apply is if you had multiple terms. If let's say we had square root of 5 plus square root of 2 over square root of 3 minus square root of 7. And they wanted you to rationalize the numerator. I would still use the conjugate, but I would be using the conjugate of the numerator. Like so. And then I would go through and FOIL all that. I'm going to start with the top this time because that has to work out a certain way. If I still have radicals there, I picked the wrong thing, something's wrong. So root 5 and root 5 is a 5. Negative root 5 and root 2 is root 10. Positive root 10. And then negative 2. Those cancel. 5 minus 2 is 3. I have a nice clean numerator now because they wanted me to clean up the numerator. The denominator then is simply root 15 minus root 6 minus root 35 plus root 14. Nothing combines or simplifies, so I just bring that over. And that would be my final answer. Again, after you do a bunch of these, that's going to look weird to you because I want you to have ingrained in your head, never leave a radical in the bottom. But they do want to show you that it is a possibility that sometimes you want to clean it up on the top. Okay, the reason why we try and keep radicals out of the denominator is because denominators are complicated enough as it is. To keep things easy to manipulate algebraically and arithmetically, we try to keep the denominators clean. However, when you get into calculus, sometimes you need to clean this up in order to make that, that denominator workable when we're looking for difference quotients and so on. Don't worry about all that. I just want you to know that it is a possibility in more complicated technical situations where you do want to clean up that top. Okay? So, again, always try to make those radicals go away when you're rationalizing. Remember that idea of conjugate, and as always, work hard. Let me know if you have any questions, and I'll see you next time.